Our previous two transversals to three parallel lines theorem actually generalizes very nicely to more than three parallel lines. We could have n parallel lines here. Right in this point, I have 6 of them. And two transversals. You have the transversal T that goes through these two, and the B, this transversal S that goes through these lines here. And it turns out that we have proportional length. So if we look at it this way, if you take the length from A1 to A2 and divide it, let's do it the other way around, length B1 to B2 and divide it by the length of A to A2, you get some number. And if we take B2 to B3 and divide it by A2 to A3, we get the same number. And the same way if we divide B3 to B4, that distance, divide that by the distance from A3 to A4, and so forth. And in fact, we could do it other ways too, besides the ones that I have pictured up here. You could, for example, go A1 to B1 to B3, divide by A1 to A3, or B1 to B5, divided by A1 to A5. Any of those proportions, any of those fractions gives us a bunch of proportions, a bunch of fractions that are equal to each other, and they're all the same number, some proportionality constant. So basically, all the links over here on the second transversal are just some k, or at the moment 1.62, times the corresponding length over here on the other one. In the other proof, we looked at a parallel line here. You can use that if you want to help, but we don't really need to do that in the proof. The proof can be a proof by induction on n, the number of lines there, okay? And the transversal to three parallel lines lemma provides the basis step. I'm going to actually call the transversal to three parallel lines a lemma because uh, this theorem that we're getting ready to come up with is actually a more general case, although really the bulk of the work is in the lemma, so in some sense what's coming up is a corollary. But anyway, whatever. It's a theorem, a proposition. So here it is. If we are given lines S and T such that A1 dash A2 dash A3 dash up to AN, that betweenness relationships are on T, and similar things for B1 to BN are on S, I should say, then and each of the A sub I, B sub i's is parallel to each of the A sub j's, B sub j, for I not equal to j. So S and T are transversals to n parallel lines for some natural number n. Then for every I not equal to j, B sub I, B sub j over A sub I, A sub j equals k for some positive constant k. That's the picture that we saw. There's a link to the activity. So the proof is by induction on n. We're given lines, well, given the setup, right? The basis step is by the two transversals to three parallel lines theorem that we proved in the last video. We see that B1, B2, that length divided by the distance from A1 to A2 is equal to B2, B3, that distance divided by the distance A2 to A3. And that equals k for some positive constant k. And certainly this makes the theorem true when n equals 2. That's all there are three lines. Now, for the induction step, assume that the holds for at least up to 3 for some n, and let n be n plus 1. So again, even for this situation, it holds for the first 3, so we get this result here that we have in the basis step, the stuff that we proved in the previous theorem. So the two transversal to three parallel lines theorem applied to T and S. To these transversals, A1, B2, these parallel lines, A1, B2, A2, B3, And A and Bn concludes that, well, then here if you just take those three lines, we can apply the theorem. And so we get K is B1, B2 over A1, A2 equals BM, BM plus 1 over AM, AM plus 1. And so the theorem is true for N equals M plus 1. Okay. And of course, that's also true for, well, it's just all of these have the same ratio. So by the principle of mathematical deduction, the theorem is true for all natural numbers n greater than or equal to 3.